All right, I'm going to go ahead and get started, even though we have another minute. My name is Chris Kaler. I'm very happy to have some guests here today. This is our mid-semester presentations for graduate projects. So if you are a guest, you're going to see real live colleagues of yours, or if you're not a graduate student thinking of being a graduate student in the fall, these are the students that are currently in the course presenting their projects. We do this every midway point as well as at the end of the semester. So you're going to get a chance to see the very beginning of the class, and then we're going to get right to the projects. So just a few announcements. The agenda I'll go through in a moment, and then we'll get started. So for those of you in the class, next week we have Kathy Schimmels coming from JPL. She's going to be talking about mission operations. She's a real life mission operator, including a rope clipper and things like that. So why do we need to talk about mission operations? Because that's your end user. No matter what your mission is, you need to know how to do mission ops. And so it'll be a good presentation, a great presentation. And then week 10, of course, is spring break. If you didn't know that already, it is spring break coming up. Let's see, peer evaluations are due tonight at midnight. So please complete those. A lot of you have already done that. Again, you have to do it for every one of your team members. And you do need to be logged into the your CU account to access that. So if you're having issues with that, that's probably the issue. So please do that. And you can find the link on Canvas, or you can scan it, but don't do it now because you're here to watch presentations. Okay. Any questions before we get started? So those in here for the guests, I'm just going to briefly go over what graduate projects is, and then we're going to get into the presentations. So if you're thinking about being of my guests, are you already graduate students? Raise your hands. If you're not, can you raise your hands? Okay. So as a graduate student, you can get your master's degree in 3 different ways. You can write a thesis, you can take a bunch of extra courses, get a certificate, or you can take graduate projects, which is a 2-semester requirement. And once you've completed that 2-semester requirement, you are just the rest of your coursework, and then you're going to get your master's degree. In this graduate projects course, we actually work in a real world environment where you're working to learn about project management, systems engineering skills with a faculty advisor on an actual project. So that is a really great experience. It's different than senior design in that it's much more focused, intimate, I would say, with the research you're doing and a faculty member in terms of what you're getting to work on. And you get a great and hopefully positive project experience. There's 2 semesters. You can take them starting in the spring or the fall. You don't have to take them concurrently. You can take it in the spring. You can take it next fall, wait a whole semester, take a semester off, and then come back and finish your 2nd semester. There's a lot of flexibility there. It's hands-on and engaging and fun, in quotes. I'm just going to show you 1 minute of one of the projects from last semester. So okay, the sound isn't coming through, but it's all right. Great acting, Kyle.
Has this ever happened to you? Hi, I'm Ben Ford, project manager of Team Max. If you or a loved one has been injured in an EVA incident during a simulated spacewalk and you're looking for a place to find treatment, then we have a product for you.
I like how you kept your arms straight like that for a while.
You need help.
Where are you going? To the Mars Emergency Clinic or the back.
Still breathing. Are you feeling any better?
I'm feeling great.
Okay. So that's an example of one of the projects. And there's lots of great projects. At the end of our presentations today, which by the way, each presentation is about 12 minutes, so 10 minutes and then 2 minutes for questions. And we're going to get through all of them here in just a moment. In the midway point, Professor Akos is going to come down and present 2 new possible projects for the fall that he'll present for those that might be interested. And then again, we do have a audience participation, not for the guests, although you can do it if you'd like. If you would like to participate, you just need to scan this QR code and you would evaluate each team's performance, not your own team. And then we'll take sort of a peer evaluation of how each of you did. The top 2 teams get an extra set of points on their overall score. And then you, by participating in each of them, get extra credit. You're graduate students, you're not as worried about extra credit, but it's fun to see what you all think of the different teams. All right, with that, are we good to go? Any questions? All right, well, let's get started with Maxwell. So if Maxwell would come on up. There are multiple mics, but you do need to use a mic. There is a remote if you'd like to use that. Wow, you guys. Okay.
So I hand the mic to you.
Yes.
Hello. It works. Okay, great. Cool.
Oh, there's no order. This is chaos.
We're gonna hope for the best.
Okay, great. You all ready? Gosh, it's like half the class.
How do we like, oh, just like
You can
that.
use this or you can.
Okay, cool. Okay, okay.
All right,
Good to go?
good to go.
Okay. Okay, hi everyone. So we are the Maxwell Group and we're gonna present what we've been up to this semester. So as an overview, we're gonna do an overview of the mission, org chart, semester goals, deliverables by subteam, and then project concerns. So we'll start with the overview. Maxwell stands for Multiple Access X-band Wave Experiment located in Leo. Basically, we're going to be designing a 6U CubeSat, and it's going to be completed hopefully this year. And the main goals of the mission are to test an on-orbit chip-scale atomic clock, demonstrate high-rate communications using code division multiple access, and characterize the performance of a T-Dagger antenna, and then demonstrate a student-built ADCS system.
Oh, I didn't realize it was like this. Okay, so to introduce Maxwell ConOps, after deployment and deployment from our launch vehicle, we'll enter a commissioning phase. This is where we test out all of the spacecraft's vital subsystems just to make sure everything's working okay, as well as deploy all of the necessary components of the spacecraft, like the solar panels and the UHF antenna. After this, and ensuring that the spacecraft is alive and well, we'll enter nominal mission operations and start with our very first experimental phase, where we will demonstrate our experimental X-band CDMA downlink capabilities. Following this, we will move on to the, oh, this is blocking the thing. We'll move on to the CSAC experiment, which is the chip-scale atomic clock, where we will seek to characterize the Allen variance of the clock on orbit before entering our final, our final experimental phase, where we will deploy the T-Dagger antenna, which is that large yellow square there, and we'll try to characterize the gain pattern for the antenna while it's in orbit before we finally deorbit ourselves. So in this table, you can see all of our top-level mission of requirements. MO1 and MO2 both pertain to our X-band downlink requirements, where MO1 refers to the expected data rate that we hope to see, and MO2 refers to the CDMA performance of the both X-band antennas as well as the X-band radio. MO3 is our objective to characterize the Allen variance of the CSAC on orbit, and MO4 is our objective to successfully deploy and characterize the T-Dagger.
Alrighty, I'll talk through our team organization. So all of our students are enrolled here at CU Boulder, and these are some of our stakeholders, which are the Air Force Research Laboratory, University Nanosat Program, Blue Cubed, and MMA Design. And this is a image of our organizational chart, which just shows the breakdown of all of our students, where they're located, which sub-teams. We have, I think, 15 students that are enrolled in the class. We also have some student volunteers, which you can see on the chart.
Hi, so I'll be talking through our semester goals. Right now in the project, we are in phase B, working towards our pre-integration review for fall of 2024. In service of meeting that goal, we are planning on completing the complete charge cycle tests, long-range communication tests, the command execution test, and the ADCS verification test all in this semester, only leaving the day in the life test to be completed next. Now we'll move on to the subsystem deliverable updates.
Okay, first up, CDH. CDH stands for Command and Data Handling. So updates, we tested and verified the ADCS data dump. We completed command and execution test. The first command and execution test, which is basically checking if the CDH can talk to the ground commands that are being sent from ground. And apart from supporting comms and EPS, there were some minor issues on the CDH software, which we fixed as well. Semester plans going forward, we have 2 more ADCS functions to complete, and then we'll be done with the ADCS interface and move on with the PLDC interface. And complete the rest of the CETs, because CET is one of the 5 UNP tests that are required to be completed. And that's all for CDH.
As for the EPS, which stands for the electrical power subsystem, we have completed the fabrication of the battery packs, as you can see on the image. Then we have gotten approval by the UNP, which is one of our shareholders, to approve the inhibit circuitry. And we have progressed on the complete charge cycle test, which is one of the big tests to complete this semester. And the plan for the semester is to finish the complete charge cycle test. In order to finish it, we're currently working on evaluating the hardware functionality of the test and coordinating with the software team for the EPS telemetry. And finally, update and enhance the test procedures. Secondly, we're gonna perform hardware tests on the EPS inhibits that has been approved by the UNP. And finally, we're gonna integrate the solar panels loader boards to the spacecraft. Cool.
On the comms or communication side of this project, we have, as of today, actually finished completing the first 2 of our simulated comms tests. And because of that, that means we have a completely working comms ground UHF ground control system from our ground control software called Hydra all the way to the spacecraft CDH software. So that means that our semester plans are going to be to finish our simulated comms testing that will involve over-the-air RF testing, and then to begin developing the actual ground station hardware we'll be using on orbit for on-orbit operations.
So for the structures updates, we've worked a lot on doing EDU assembling. And the goal here is basically once all the subsystems have done their individual component testing, we can be confident they can integrate everything into the structure and that everything fits. And we've also completed some analysis work this semester to meet some of the requirements we have. And I guess moving forward into the rest of the semester, we identified some manufacturing goals that we have to take care of, as well as updating our documentation so that all the teams can fit into the spacecraft once they're ready.
Okay. On the AIoT side of things, we've been working on integrating all of the ADCS hardware onto our flat sat. So that is our reaction wheels and torque rods. We were plagued for the longest time with an issue with our reaction wheel enable pin not pulling enough voltage. We've pulled a resistor off of that to fix that. We've been revamping our documentation to accommodate new members, getting them up to speed. For the rest of the semester, we plan on starting minimal communications testing just after spring break. We have been chatting with LASP and their heliostat to figure out how we can incorporate that into our sun sensor testing procedure.
And then later this semester, we will be working on integrating our EDU so that it's ready for our Helmholtz and hang wire testing to help characterize our magnetometers and reaction wheels.
Okay, so for thermal updates, so if you see the model right there on your right-hand side, so we are done with updating the model with the current revision of CAD model on for structure stream. And then we are done with component thermo-optical testings for properties updated for the table that is in line with the thermal model. And then we are done with thermal coating sensitivity analysis. So moving forward, we have the task that needs to be done. So first one is finishing simulation of time-dependent heat loads, which are based on power budget mode and duty cycle of components. And then after that, we have to perform the higher fidelity analysis of board concentration heats and the tumbling during the deployment. And then we have to prepare documentation on the tests that further, we have to prepare the documentations for the tests like thermal vacuum testing and thermal balance testing.
Okay, so for ADCS, some major updates for the semester. We've integrated a lot of important parts, the reaction wheels and the GPS board, namely those two. We've also created new ADCS boards, so that's really cool. And okay, so the next thing for the rest of the semester is we're gonna finish and test all the GPS functionality, and we're gonna continue testing the software. Okay. Project concerns. Okay, actually, so for ADCS, we are finishing and testing software. It's going to take a little bit longer than we originally anticipated, but we're mitigating that risk by onboarding 2 new members to help, or we have already onboarded 2 new members to help.
Yeah, and then CDH also has some, risks associated with it. We got some software delays for the magnetic execution test just because, we got to look through all the individual subsystems, make sure they're doing okay before we integrate everything in the flat stat. We also, we're always looking for extra hands to code an embedded C, something with Maxwell. We're always needing more C coders. So just trying to get some more hands on in here. And then I mentioned it for the CDH specifically, we might have a board revision potential, just because the CDH, it's the brains for the spacecraft. If any of our peripheral boards change, CDH has to change to match it. So we're mitigating this by, thoroughly using a block diagram, knowing where all our traces and our lines go, doing individual testing of all our individual boards and making sure that's all doing really good before we add in for a full day in the life test. So I will pass to comms.
On the technical side for comms, we are at the point in our testing where we're going to move into longer range testing and integrate our antenna, but we're not quite at that point with our antenna development and testing. So that's going to become an obstacle. We're going to be allocating some more resources to that effort here in the next couple of weeks. Some of Maxwell's science also prevents us from being able to license in the amateur band. That makes licensing and ground station usage much more complicated. So that's been an obstacle that we've been working on for the past semester and last semester too. And the non-technical side, we do have several team members graduating or moving to a lighter workload next semester. So there's potential for a knowledge vacuum there. So we are looking for anyone who's interested in RF or communications or ground station software or hardware.
For the structures teams, one of our responsibilities and corners is transition of knowledge and preservation of CAD models. So as you may all know, this isn't a semester-long program. It goes beyond that. So documentation and mentoring new students takes priority at the end. And additional manufacturing in the sense we are modifying many CAD models, like modifying in the sense we are modifying few adding brushes and washers to few CAD models, and we also entirely modifying few CAD designs like mechanical ground support equipment. So that's it for the corners for structures team.
I'll finish up here with the thermal project concerns. I mean, these guys have kind of already hit it, but revision control and knowledge transfer is huge on a project like this. And unfortunately, the thermal team has spent about the semester up until this point partially redoing work that may have been completed to some extent in the past. So we're implementing revision control, which is a big thing from Professor Kohler here. And we're excited to actually maybe not have to, be doing work that was already done in the past. But the one thing that I wanted to bring up is that validation from a thermal perspective occurs very late in the development cycle. Your satellite is basically built by the time you're able to actually test whether or not it's going to survive in a TVAC. So we just want to make sure we get the simulation as best as we can. And that's all we have. Thank you very much.
Next team is the Astra team. You can have them come on down. And just as a reminder, again, you can participate with the URL or the QR code there if you'd like to rank presentations.
Two. Just one, sure. We can do two. Give Brett one. We'll do like a sandwich pass off. Yes.
Test.
Just. I need to stop. Helps if you might, if you're in your order. Maybe, sort of. I don't know. Yep, you stink. I think so. Always. Wow, this is really. Yeah, but we're going for the, it's our audience.
Oh, I see. Yeah.
Colonel Boss is elevated.
All right. Good evening, everyone, and thank you for attending the Spring 2024 midterm report for the Advanced Space Transit and Residency Architecture team as part of the Human Spaceflight Graduate Projects. My name is Brett Bennett, and I am the project manager this term. Over the course of the next several minutes, we're going to introduce the project. We're going to provide a project organization. We're going to have a look at our progress on our deliverables, and we're also going to look at the concerns for the project as we move forward. And we're going to wrap up with questions as time allows. And I'm going to pass it to Kylie for our project introduction.
Thank you, Brett. Like he said, I'm Kylie. I'm our deputy project manager. I'm going to talk about our project purpose. So ultimately, the motivation for this project is to enable safe human Earth-Mars transit as part of the larger NASA architecture for Artemis and future missions to Mars. Ultimately, the purpose is to design a Mars transit vehicle because they'll be required to support long-duration planetary transit in the future. And as the Human Spaceflight Graduate Projects typically does, is try to look to the future of what the next projects will be for NASA and kind of prepare us for what's going to be coming in the next 10 to 15 years. Our goal for our specific project is to develop a conceptual design of a Mars transit vehicle and conduct a mock-up build for human factors testing of this design. I will pass it to Avery for our concept of operations.
So to take an overview of what exactly this project looks like, it's basically divided into 5 major phases. At this point, multiple launches will go to assemble these modules up in the low Earth orbit. They'll then go over to Mars orbit, where it'll rendezvous with the descent ascent vehicle, where the DAV land on the surface. The crew will occupy the SHAB, or the surface habitat, for a while until they return up to the Red Hound to transfer back to Earth and eventually arrive. Red Hound and Team Astra is actually particularly focused in the 3rd phase of this mission in that transitory period, which is what the rest of the presentation will be about.
I'm Sebastian. I'm the systems engineer. So I'll go over quickly our requirements that we've been following. So our big functional requirements we've kind of developed is to launch Red Hound into low Earth orbit. From there, we're going to assemble Red Hound. We'll then transfer Red Hound from low Earth orbit to low Martian orbit. We'll then be supporting Martian operations while at the low Martian orbit. We'll then transfer Red Hound back from low Martian orbit to low Earth orbit. During the entire time, we're going to enable Red Hound's use and reusability and ensure its safe operation. And then we're going to make sure that we keep the crew alive, healthy, happy, and productive. And I'll now pass it to Alicia.
All right, hi, I'm Alicia. I'm here to present the project organization. So our project is organized at the top level. We have Colonel Voss as our senior engineer. We also have Rick Heap as our senior manager. And then our managerial positions for the project are divided into 4 categories. And then we are also divided into sub-team leads and also our sub-teams. And now I'll pass it off to Kin.
Hi, I'm Kin. I'll be talking about the deliverables progress. So the spring 2024 deliverables are all listed here. You can see that 1 through 4 have all been completed, with number 5 in progress and still to do 6 and 7.
Hello, I'm John. I'm the structures team lead this semester. And this is a basic top-down overview of our conceptual design. As you can see, the Red Hound vehicle, or the vehicle that we named Red Hound for this transit period, is shown here. And looking top down, the orange module is the propulsion module, followed by 2 pink connecting nodes, which are shown here, and then under this yellow. And then our red module is the habitat. Our blue is the logistics module, green is the laboratory, and the purple is the EVA airlock. And then we have our solar panels and radiators shown on the sides. And I'm going to pass it off to Charlie.
So having completed our conceptual design of the entire vehicle, we're going to be moving into our mock-up and human factors testing. For that, we're going to be focusing on our habitat module, which you can see in more detail here. We've got CA crew accommodations in purple, life sciences and life support and environmental control in green, and G&C in blue. So you can just see some of our more important aspects of the habitat module. We have sleeping quarters, medical supplies, a galley, a bathroom, exercise equipment, and so on. And I'll pass it to Tucker to talk more about the mock-up.
Sweet, thank you. Now moving into the mock-up build, on my left, you can see the conceptual design for the mock-up build. Then on the right is what we've done so far. We've just put in the main structure beams as well as the cross beams. And one thing to note about this mock-up build is that we are trying to get these modules to be, well, modular. So they're going to be in 24 inches, 36 inches, and 48 inches to accommodate for all the different sizes of each subsystem's console. I'll pass it off to James to talk about human factors.
Hey there. I'm James, I'm the human factors lead. We're going to be doing some human factors testing of this physical mockup of our habitat module, which is based on the previous home mockup that's been in the high bay for a while. We're going to be doing our day in the life testing, running through a simulated crew of 4 through a day in the life scenario where they'll wake up, they'll have a meal, they'll communicate with the ground, and we'll also have some unexpected happenings to deal with to make sure that our internal volume as well as the layout of the habitat is well suited to the tasks that they'll need to complete during transit. So we'll be evaluating our layout design, keeping in mind our considerations. We are obviously testing in 1G and not in 0G, which has a pretty substantial effect on the layout, but we're doing our best to keep all the interfaces that the crew would interact with on the walls, and then we can just sort of say that the rest of them are on the ceiling and floor, but we will have hands and footholds to increase the fidelity there. If you do want to participate in this, please let us know. Feel free to shoot me an email and I'll get you on our mailing list. And I'll pass it off to Catherine to talk about some project risks.
Hi, I'm Catherine. I'm the environmental control sub-team lead. So just some project concerns schedule. We just had our design definition review last week, but in parallel, we're also doing the mock-up build, which we need to finish by the end of March. And we're still trying to procure all our materials for that. And then for the design, we're transitioning from the conceptual design to a low medium fidelity physical design for the build. And then as James mentioned, we have to build in 1G instead of micro G. And any questions?
Yeah, that is a great question. It's something that is still being worked out right now, but the way that the Human Spaceflight Graduate Projects is set up is that we start kind of like a high-level conceptual design this semester and do some sort of mock-up, and then you can either take iterations of this design and based on test results kind of redesign and refit, Or since this is such a large vehicle and we're only building the habitat module of the vehicle, there's a chance to redesign and then build a new module from this vehicle. Chronovos likes to keep it such that it's a good process for students to learn what's up and coming. So there's always the chance too that he thinks of a new project that's also useful for student education if they want to get into human spaceflight work. So it's still being decided right now, but hopefully we will know soon. It's always really fun though.
Any other questions? Nice job. Thank you very much. Professor Akos, welcome. Are you ready? All right. We're going to take a break and go from current projects to potentially future projects, depending on whether or not we can get enough students engaged with some of these ideas. So I'd like to welcome a future presentation here for Professor Akos.
So I was asked to get involved with graduate projects next year and kind of toss together a couple ideas for 2 different potential projects. These are still very much being discussed, so the ideas are somewhat preliminary, but I expect to kind of refine that over the summer and then offer them during the next academic year. 2 main ones: radio telescope investigation optimization, scientific GPS GNSS monitor station. I am a GPS person, an electrical engineer. These are stemming from different research elements I've been working towards. One thing I've always done throughout my career, use big telescopes, big radio telescopes. On the right here is one up at Table Mountain, which NTIA ITS owns and operates. They have 2 dishes over there. You might see them as you go north along 36 up to Lyons. They're kind of tucked in there a little bit. There's actually a radio astronomy group, Deep Space Exploration Society, which has a 3rd parallel dish down in Haswell, Colorado. And they've been going through the process. That's the middle picture right here of renovating that, getting it up to speed. And I do an awful lot with that for space communications. Really, I look at GPS satellites, but it's used for LEO. So they've done an awful lot of work in terms of putting these pieces together. It's a unique place down in Haswell, Colorado. It's very radio quiet. It's a great place to do kind of work. So there's multiple projects this could go. I'd point you to this DSES science page if you're interested in them. But possible projects, you know, a big parabolic reflector, all it is a reflector, and it all goes to a feed point right there. So designing some of the feed points that go there for X, S, L bands are something we want to do. They've talked about a meridian drift scan to go through a radiometer, to go through enable sky surveys at different wavelengths. One problem, does anybody know where Haswell, Colorado is? There you go. It's pretty remote. I've been there one time. So it's a real hassle to get there. I used to love to go to Table Mountain, 10-minute drive. Haswell is about 3 hours plus away. You have to go down and get there. So why not automate things? You can control the antenna, put cameras in, everything else automatically. So we could do that kind of piece, put this system together so we can control the antenna and do these kind of monitors without actually being there. There's a little hangar, they have radio, high-speed internet right there. So it's a pretty remote place, which is great for radio astronomy, not so great for being in person, kind of tackling some of these projects. So that's where it's at. So the different ideas we can work with, I mean, working with some of these big antennas is pretty amazing. This is a 60-foot antenna. In comparison, I think there's one I worked with at Stanford, which is 100-foot. The biggest one in the US is 300-foot in Greenbank, West Virginia. I've done some work there, and I guess there's a real big one in China right now. These are all steerable radio astronomy telescopes. Second topic. This really has been motivated by a couple of students here. If you think about GPS remote sensing, there's this Guardian project, which has really been initiated by JPL, and they are really looking at ionosphere for natural hazard warning. So they have different examples on their webpage for earthquakes, volcano eruptions, geomagnetic storms, tsunamis. It is possible to look at what is happening in the ionosphere to get a predictor for these different natural events. And JPL has investigated this early. They have this Guardian network, and really that's what they're doing, is they're taking measurements of the ionosphere to see really what happens, using those, digesting those measurements to do some type of prediction. So that's kind of the link for those pieces. The problem they have, if you look down at this bottom right figure right here, this is their reference stations. Their reference stations typically are about $30,000 to build. It's a very high-end survey grade GPS receiver, which is kind of depicted right over here. And for a long time, that was the best you could do in terms of getting these GPS measurements. However, now your phone likely gets dual frequency GNSS measurements from 4 different constellations. And we can also buy these very inexpensive receivers for about $200, connect to a Raspberry Pi and antenna. So instead of a $30,000 station, I can almost make a shoebox size station, which would be disposable. And I get a much denser measurement of the ionosphere, significantly benefiting what JPL is trying to do with this Guardian network. So those are my 2 project ideas. One is working with the big antenna. The other is, hey, what can we do with phones? And I'm working with Google on some of the phone pieces. We've done an awful lot of work with some of these lower cost receivers. You know, that's probably a $500 node, shoebox size, zip tie it down to the rooftop and give the same measurements, but a much denser network. So JPL is interested in trying to work with them a little bit. 2 ideas for projects for next year. Questions at all? Make sense?
Should have mentioned at the beginning that even though you're on a project, if you're first semester graduate projects, you can transfer projects. So if this is something of interest to you, that's always a possibility. So
yeah, and it's open to refining I'm open to refining what the ideas are. Again, 2 projects will be solidified more over the summer. Depends on what interest is, depends on what really happens with that. But I tossed out 2 what I think are pretty neat ideas. Thanks, everybody.
all right, thank you very much. All right, moving right along. Suddenly we're ahead of schedule. So let's bring back the first team to get their questions in. No, I'm joking. Okay. All right, ACES, would you please come on down? I'm sorry, you were looking at that QR code. Anybody get that? Heiko, you got it? Okay. You don't have to rate Professor Akos's talk. All right.
Hello, everyone. My name is Jeremiah Munson. I'm the project manager for the Attitude Control for Precise Sciences, or ACES project this semester. So in this presentation, first we'll go over a brief overview of what the project is and the team organization. Then we'll go over this semester's milestones and our current progress. And then we'll end with a few of our project concerns. And I'll hand it off to Nicole to go over that project overview.
Hey everyone, my name is Nicole. I'm just going to go over the motivation for this project. So something the industry has been thinking of for a while is, can we do astrophysics with CubeSats? You know, we have these big billion-dollar telescopes like JWST, but can we do stuff with smaller form factor satellites? And so LASP and Aerospace has sponsored us to develop a standalone ADCS module that can eventually give us the accuracy we need to do astrophysics. So like I said, our project is essentially a standalone ADCS system that gives us high accuracy inertial pointing. And at the beginning of the semester, our status has been that we finished our Delta PDR last semester. We've created our system design and selected our hardware components. We have a functioning simulation, and we started our flight software library in C. And we determined the ConOps of our CubeSat. And now I'll hand it over to Anshul.
Hey, so the top level requirements that drive our project are actually going with the motivation. That's the astrophysics level applications of the CubeSat. And that actually drives the inertial pointing accuracy that is required for the project. That comes down to 3 arc seconds, 1 sigma. Another top level requirement is the project is just an ADCS system. It's a standalone system that can be applied to any configuration of CubeSat. That depends on the customer. And it should be pretty lightweight, just under a kilo, and occupy 0.5 U of volume. The organization of the team that we have currently is Jeremiah Munson. He is the project manager this semester. Alex Baim, she is the deputy project manager. Again, Jeremiah is the software systems engineer as well, and Alex is the lead simulation engineer. We also have Julian Lema. He's the systems and hardware engineer on the team. He is not currently present today here with us. Hunter Singh is a volunteer. He is working as the integration engineer. Nakul Gupta, he is the lead flight software engineer. Galen Savage is the simulation and controls engineer. He's a contractor on the team. Anirudh Rattagi, another simulation engineer as a volunteer. And myself, Anshul Jain, I am the flight software engineer on the team. I'll now hand it over to Alex.
Hey, I'm Alex. I'm deputy project manager, and then also the lead simulation engineer. We organized our work this semester into 3 different reviews to present to our sponsors. The first one is the software interface design review. Jeremiah will talk a little bit more about that. This was defining the interfaces that would be between our sim and flight software, and then also the interface between our module and then the main module or the main computer for the CubeSat. And then the second review is the FlatSat integration plan review. That's coming up in about a week. And it's our plan for our FlatSat development and then our testing of the FlatSat. The FlatSat is a test bed for our module. And finally, we'll have a FlatSat and flight software and simulation progress review, which will just be presenting improvements that we've made to all of our simulation and then flight software repos this semester. This is all leading up to making a FlatSat so that we can do testing and have a proof of concept for our module in the future. So next semester, we're looking into procuring components and actually putting together the FlatSat. Here's a little diagram on our progress. Yeah, we're almost done with the interface design review. More than halfway done with the FlatSat integration review. It's a little misleading, but we're only accepting like completely finished tasks for this part. So then the next one is the flight software and some progress review. We have a lot of time for that. So moving on.
So the interface design review that we did a few weeks ago, presented to the sponsors, was specifically focused on defining the packets of data that go between the ACES module and our simulation or the CubeSat bus. So it's what data is going into and out of the system. And the packets that were defined for this review, these aren't the finalized packet definitions. They're going to keep evolving as the project continues and flight software continues development. What was really important was defining the packet headers. So that's how you identify what a packet is. The ending of packets, which allows you to make sure that the bits that you received were the same as the bits that were sent. And then also our approach to defining packets. Are packets too big? Are they too small, too specific? So we were able to get some really good feedback from our sponsors, and we updated our documentation. And right now, we're just waiting on one more signature from one of our sponsors. And I'll hand it off next to Anshul.
Okay, so the next review coming up for us is the FlatSat integration review. And here at the right, what you can see is the CAD model of the actual ADCS module that we have designed. We have all the major hardware components over there. For the FlatSat, in this semester, we'll not be incorporating all the hardware components. We have chosen the magnet orcas and reaction wheel trade studies are done, and we have also conducted the DSAT analysis for the reaction wheels. The sun sensor coverage tool is a tool that tells you how much percentage of sky will all the sun sensors actually cover on the CubeSat. That is also ready, and we have 100% coverage. The to-do tasks that we have for this review are finishing the interfacing document and the hardware V&V document. I'll hand it over to Alex.
So we have a lot of tasks for flight software and sim that need to be done over the course of the next however many semesters. And so the goal of the flight software and sim progress review is to just show the progress that we're making this semester. So some of these tasks are not related to each other necessarily, but they're all working towards the same goal. But we do have one big focus for this semester, which was to create a flight software library and then integrate it into our sim so that our sim can run the flight software and get telemetry back from the flight software. We're working towards that. So yeah, we already created the flight software library. And then we created a module in our simulation that pretends that it's the main flight computer telling our ADCS module what it wants the ADCS module to do. Those are checked off. Next is to connect that flight software to our simulation and then start replacing our models in sim with that flight software library. And then another task we have is to do course navigation and some more navigation work in our simulation. Yeah.
So our two biggest project concerns right now is our funding and getting NDAs. With our funding, with our current projected timeline and the cost of components, we're coming up a bit short. It's mostly because ADCS components some of them can be very expensive. So if we cut out some of the components for FlatSat, we should be fine, but ideally we would have all of the components in the FlatSat. And then acquiring NDAs, we're not allowed to sign NDAs on behalf of the school or a project as students, but a lot of companies require NDAs for detailed documentation and even purchasing components. So those are the two biggest concerns that we have going forward. And that's our presentation. Do you have any questions?
Question? I think you answered them all. All right, thank you again. Walk off the stage. Thank you. All right, we have two more coming up here. So SwarmX. Is there any pizza left back there? There's also the gluten-free stuff if anybody's getting desperate. They just put sauce on the cardboard and put it in the box. So, all right.
Hey everyone, thank you for joining this presentation. I'm Raj Kedia. I'm the lead AI&T engineer for this SwarmX project. Sweet, thank you. So yeah, moving ahead. This is our team, us three and Connor up there, but we are a part of a bigger team here at CU. So our PI is Dr. Scott Palo, who is also the PI for the Maxwell team, which presented earlier. The project overview. So SwarmX stands for Space Weather Atmospheric Reconfigurable Multi-Scale Experiment, big abbreviation. And it's a collaboration between 6 different universities across USA to develop 3 3U CubeSats that will be flying in the lower Earth orbit. And to talk about it more, I have Matt over here.
So the objectives of SwarmX are threefold. We have science, engineering, and education objectives. To accomplish our science objectives, we're using the 3 3U CubeSats, as Raj mentioned. I don't know where he went. And we're going to be studying the equatorial ionization and equatorial thermospheric anomalies. And we're going to be demonstrating some cool engineering feats like formation flying, autonomous collision avoidance, and UHF crosslink between the 3 CubeSats. So here's just a quick video of what some of the formation flying will look like if it plays. It worked when I tried on my computer, but if it doesn't work, it doesn't work. Yeah, so in this, we have a CubeSat in the middle called the Chief, and we have the two other CubeSats essentially making an orbit around that central CubeSat. And just to go over the ConOps for the mission. So after deployment, we have about a month of systems commissioning, followed by 2 weeks of GNC experiments where we'll be doing those feats like the formation flying and collision avoidance. Following that, the CubeSats will get about 1,300 kilometers between each of them and conduct the science mission, followed by a couple more weeks of GNC experimentation After that, our primary mission is completed. And then we have an extend mission that would include another segment of science and then GNC experimentation. So next I will hand this off to Connor to talk about the requirements.
Yeah, well, so for our principal system requirements, they are what you'd probably expect them to be for a CubeSat. We have to fit in our dispenser. We have to make sure we don't brown out and stay power positive. We have to adhere to a lifetime orbit, so we comply with any FCC requirements for staying in orbit and deorbiting quickly. And we shall adhere to all of our preferred practices so we know that we're built all right. One that was a recent, very important thing that we've noticed is that all uplink communications must be encrypted, as well as all intersatellite communications must also be potentially encrypted in order to comply with export laws and some other stuff. Next slide. And going here will be how our project is organized. Next slide. So here's the full team. SwarmX is a multi-college program. So as you can see, we collaborate with schools all over the country, from Georgia Tech to Olin and Massachusetts. Yes, I won't bore you with every single detail, but the majority of it is focused on CU, though we do have to take into consideration that a lot of our other sub-teams are at different universities. Next slide. Here's our full CU team org chart, with Colton Brown as the lead systems engineer, and I'm all that needs to be updated. Well, I'm actually the thermal lead. Colton doesn't hold that title anymore, but this is the breakdown for our team. As you can see, we're mostly a volunteer force, so we'll take any and all project graduate enrollees we can, just to keep consistency in that, because one of the problems we've had in the past is just volunteers. Other people have other times, and it's nice to know that I'm going to get my teammate for 15 hours a week at a minimum for a class. And next up, we will have Afri.
All right, so as far as what we've accomplished this semester with the Science and Instruments team, so we do have 2 instruments. We have iSense, which features a Langmuir probe to measure plasma densities, and it also has a magnetometer with it. And then there's also FIPEX, which will be studying neutral oxygen densities. So this semester, we've completed thermal characterization testing with the Langmuir probe EDU. So that included spending a lot of time sitting next to a thermal chamber to see how the Langmuir probe is affected by different temperatures. And we've also completed updating our flight equipment list for the instrument deck and organized all of our equipment into one place rather than being scattered all over. So right now, we are currently in the process of developing the instrument deck assembly and integration procedures. Following this, we'll actually be assembling our flight units and then conducting acceptance testing with them.
So for the AINT, which stands for Assembly, Integration and Testing, we completed our fit check for the entire assembly. A fit check is basically to have a mock-up assembly of the entire structure and see how the things are working out in the entire structural assembly. Right now, we are planning for another fit check with mock-up wires, where we actually put up some string wires in the entire assembly and see how the spacing goes and everything goes about that. But a lot of work right now is being done for documentation as to developing our assembly procedures and developing our testing procedures, so that before we move into our PIR, we can definitely complete those. And to do those or to perform those tests, we have to integrate a flat sat. A flat sat stands for flat satellite. Basically, you're trying to mock up an entire structure of the satellite into a flat board, and you put up your entire flight unit or your engineering units and integrate them together and perform a lot of testing on those particular components. So these are requirements or tasks for the AINT. Moving on to thermal.
Awesome. So as thermal team lead, our our job is to make sure the thermal model is always up to date. And this semester, we've updated the thermal model contactors and heat loads, which is really just a fancy way of saying we know how much heat each component is going to, we verified how much heat the component is going to produce, and we verified how it's attached to the spacecraft. As far as in progress stuff goes, we have a few more components we need to update, namely the battery and the instrument panel. And a common theme of many graduate projects is make sure the documentation's up to date. So when all of us inevitably leave, there's not some poor soul who has to come in with this on their lap and be like, I have no idea what any of this is for, as many of us have experienced. As far as to do, once my thermal model is updated and I trust that everything's right, I'll be able to run orbit and coding analysis to see how sensitive we are to different orbits for our mission, and as well as what different coatings we can apply to the spacecraft can change our thermal profile.
Attitude dynamics and control system. So this semester, we've really been focusing on picking up the slack because this subsystem did fall behind back in last spring. The former lead was located at Georgia Tech, but all the hardware is at CU, which caused some difficulty. So I took over as the ADCS lead this semester. So we focused on debugging the interface between our attitude control system, which is the exact from Blue Canyon, and then the RDP/the Cosmos software, which allows us to simulate the satellite being in space while we're just in the lab. This is what caused the problems a year ago. So we were able to figure out what was going on with all of that, as well as executing acceptance testing on one of the exact units. Because we have our 3 cube satellites, we do have 3 exact units. So in progress would be finishing up the acceptance testing for the other 2 exact units, as well as creating some comprehensive documentation for all of these procedures, because this did cause a little bit of a slowdown when things were transitioning over to me. Just gaps in knowledge and things that had been lost over the last year or so. And then still to do, ideally, if things happen on schedule this semester, we'll have finished some base level unit testing, as well as some unit testing with the CDH subsystem, so that the exact is in a better place for full integration. And some challenges we've been facing that have been touched upon is we're a multi-university project, so communication can be very difficult. For me, with the ADCS team, we are now located fully at CU, but it was hard to handle that transition because everything was coming from Georgia Tech. So all that past knowledge is still at Georgia Tech. We also have some trouble with recruiting and student turnover. So if people want to join, that would be awesome. We do have a lot of people graduating. And also just schedule shift, things take longer than you expect. So originally our launch was hopefully going to happen March 2023, but we are now March 2024, but hopefully nearing the end. Thank you. And any questions? Well, it's March 2024 now. Like, no, not, yeah. I mean, we're already a year past the goal. That was what I meant to say.
Any questions?
We could. It just wouldn't work.
All right. Well, thank you again. Great job. All right, our last presentation, again, the QR code if you're all looking for that. After this presentation, I just have a few quick announcements about the course for those that might be here and entertaining the idea of taking it, how to do that, and a little bit more about the grades, but that'll only take a couple minutes. So, all right, are you all up here, the whole team? Okay, we don't have enough mics, so you're gonna have to share.
Thank you, thank you. Okay.
Great.
Hi, guys, I'm Joey. I'm the project manager for Series behind me, or to the left of me.
I am Garrett.
Yeah, our systems engineer for the project. Yeah, we're short on members, so definitely need people on this team come next semester, especially because we're turning it over to new graduate students. Anywho, We're gonna go through standard format that everyone's been going through today, going through overview, project organization, then sliding through to the deliverables and milestones for our project this semester, and then some work highlights. And at the end, we're gonna round it off with project concerns. Alrighty, so for project overview, we are Team Series. It stands for Carbon Dioxide Environmental Removal for Extended Duration Space Flight. And we're actually sponsored by the Boeing ECLIS team. So ECLIS is Environmental Control and Life Support. And they're also investigating new advanced exploratory systems for trans-Martian habitats. So what they tasked us with is investigating new and novel approaches for regenerable carbon dioxide removal from spacecraft habitats. And keyword is regenerable here, and that means we want a closed loop system that doesn't need any mass resupply, as these systems are going to be going to Mars and back and probably for repeated use without much access to any ground support during those habitat transits. Our goal for this semester is to develop a scaled down testbed using previous graduate project testbed hardware from the team called HERD, and we're going to use this testbed to verify and validate those higher level requirements that we have for CO2 removal, which I'll get into in a second. First, I want to talk about the why this is important. Right now, carbon dioxide levels here are about 0.04% of the atmosphere. On the ISS, they are 0.5% of the atmosphere. Now, this actually gets increased in some degraded scenarios, and this can be a problem because these astronauts can experience headaches, dizziness, confusion, and just have a hard time making decisions. And you can see how this could be a problem if you can't abort immediately to the ground from LEO. When you're going to Mars and you're confused and you're on your own without any ground support, that's bad. So we want to beat these partial pressure CO2 requirements on the ISS and drive it down to about, I think it's 0.1% of the atmosphere. That's really tough to do. So that's why we're researching it here.
All right. So just to put on our ConOps real quick, basically when NASA wants to go to Mars, and that takes some time. And as Joey was saying, you need to communicate with the ground and everything has to run smoothly and the astronauts have to be comfortable and happy and productive. And one of the main things is carbon dioxide in the atmosphere. You have to get it out. 7 months there, 9 months back, 3 months on Mars. That's a nearly 2-year mission. And if anything potentially needs some extension or the astronauts have a stay at the lunar gateway, that kind of thing needs to be 3 years maybe of uptime on this system. Needs to be removing 1 kilogram per person per day of carbon dioxide. That's doesn't seem like very much, but it is when the best you can do is scrub it with chemicals. So we have to specifically research how do we get that out of the atmosphere as effectively as possible while maintaining the partial pressure of carbon dioxide at a low enough level that the atmosphere is reasonable for the astronauts and indeed ideal for the astronauts. And so basically this is effectively what is going on there. And realistically, we probably wouldn't send it to space like it says there. We would probably send it to a reactor to be changed back into oxygen. This is something that NASA tries to do a lot. There's about a reactor that was on the ISS, didn't end up working out. There were some issues with it, but they're trying and make a new one and revise the design for Mars transit. So that's one of our driving requirements is we need to somehow manage to scrub the carbon dioxide and then send it to whatever system is going to be on the back end. So yeah.
All right, so now I'm going to be talking about the top level requirements. So our Boeing group has worked a lot with the ISS CO2 removal technology. So basically they're giving us requirements that are going to beat their previously designed systems. Now that's hard to do. So our goal is to minimize consumables and maximize regenerable capabilities. I kind of already talked about that, so I'll skip through that. We also don't want to include zeolites or amines. These are the technologies that are used on the ISS right now. And the point is Boeing just wants to research something novel, to have that dissimilar redundancy for later technologies to be developed. And our formal goal for a partial pressure of CO2 on the habitats is 1 millimeter mercury or 1 torr. That's about 0.13%. Carbon dioxide on board, that's a lot less than the ISS. So if we can beat that, that is awesome. And then we're also framing some of our performance and survivability requirements based off of Gateway. So we have a without performance degradation requirement of about 3 years. Also not mentioned here is vacuum survivability for about 1 year. All right, so I'm gonna get into organization of our project. So like I mentioned, we are just 2 graduate students enrolled in this course here. So we're taking up the technical and non-technical leadership of the project. And then we also expanded out into some undergraduate independent study researchers hosted by Dr. Nabity. So that makes up the large portion of our subsystem members. And then we had those returning members as leads come in this semester and help out this new guys joining on the subsystems. Lots of opportunity for work at any level, undergraduate, graduate, even PhD research. So yeah, there's a lot of room for growth here. Our advisement breakdown, like I mentioned, we're sponsored by the Boeing Advanced Exploratory and ECLIS Group. Also, our stakeholder is CU Boulder, just because we're using their lab spaces, and our advisors belong to this school. And our faculty advisors are actually, we have two. So Dr. Nabity is our PI on the project, and then we also have Mr. Stuart Tozer from BioServe. He is our specific graduate project advisor, and he also helps us with some technical stuff too. All right, so spring semester deliverables. Following the project course, we have, this presentation here, final video to give. We also have our project charter that we had to turn in, but then we have some more specific customer deliverables. So we have weekly meetings with our sponsor where we meet for about an hour, give them quad chart updates for each subsystem. And we actually just got through our CDR last week with Boeing. They came and visited on Wednesday. Went really well. So we're going to keep progressing towards the test readiness review, which is going to happen at the end of, or at the start of April. And then we're going to be shifting into just testing phase, where we're going to be documenting all of our test results after we assemble the system and check it out. And then we're going to also be, just documenting our work for future posterity, as we're going to have a pretty massive team turnover going into next semester. Also important to note, we hope to be presenting at the ICES poster competition. I think it's in Kentucky. I forget where it is, but we're going to be doing that in July, and we're going to see the Boeing group there, so it should be fun. Alrighty, so spring semester progress to date. So we are a new project that started in the fall. So we started at very conceptual level. So we started doing trade studies for different CO2 removal technology possibilities. Then we moved into preliminary design and system requirement definition phase, all the way through to critical design phase. So now our design is ready to go and ready to be assembled with a couple tweaks. And then we're also going to be doing some test procedure development that has been underway for our system once we fully check it out. And along the way, we've been doing a lot of material compatibility testing, which I'll get into soon. Work ahead, we're going to revise our CDR design over this week so we can start fabricating our parts in-house. That involves a lot of material procurement. We're also going to continue to develop we have like a predicting, validating model called VHAB that we're going to be using to empirically input our data and have a checked out model that can, test certain parameters of our ionic liquid stream or our carbon dioxide stream, and then we can get predicting results from that model. It's all based in MATLAB. And then we're going to be doing a lot of system testing in the future of this semester and then into the summer. All
right. So this is our system process diagram. It looks kind of scary, so we're going to go look at something not as scary. Basically, all this stuff that's been grayed out over here, that's what I was talking about earlier, the backend that provides the air after it's been scrubbed with carbon dioxide to the system that would potentially send it back out or send it to a Sabatier reactor. Mainly what that entails is removing all the water from it, because Sabatier reactors can't handle water because they need to be hydrogen and methane based. But for the most part, the rest of the system is pretty straightforward. There's an absorber module and a desorber module. And the absorber module is made with this substance called ionic liquid. And the ionic liquid is just a organic salt that's liquid at room temperature. It draws carbon dioxide out of the atmosphere and bonds with it chemically as well as dissolving it. So it becomes really efficient, more efficient than you would get from just dissolving alone. And then after the carbon dioxide is in, you have to get it out. And that's what the desorber is for. And we're trying to use ultrasonic energy to vibrate it out effectively. And what that means is the ultrasonic vibration is at 40 kilohertz, and the really, really, really fast vibrations are at very low amplitude. And so it creates very small vacuum bubbles within the liquid called cavities. And this cavitation effect effectively creates really low pressure areas that the carbon dioxide can come out into where it prefers to be rather than actually dissolved in the fluid. And then those bubbles will then just be released by the fluid. Now we need a vacuum to do that though. So we have to pull lower pressure on the outside of the liquid. So that requires a vacuum pump. But for the most part, that's pretty much what it all is. There's a system that supplies the simulated spacecraft atmosphere, some the absorber module, which absorbs the carbon dioxide out of the air, the desorber module, which brings it back out of the ionic liquid, and then sends it to whatever system that is going to use it afterward, and the vacuum pump that helps that happen. It's not shifting. There we go. All right. So like I mentioned, material compatibility testing is really important because ionic liquids haven't been used much in academia, and it's not really well known what material it's going to eat and what it's not going to eat. Exhibit 1 is chemical resistant Viton O-rings immediately dissolved in our ionic liquid under 24 hours, which is bad. So if we didn't do this, we would have a system that just starts leaking very dangerous chemicals all over our lab space. So it's good that we're doing this testing early on in the tabletop testing regime. Also, another thing here, it's kind of hard to see with this this lighting, but we had some epoxy that we tested and it immediately started flaking and losing its outer core, which is also very bad if you're trying to bind any materials together. Hey, Garrett, it was. Yeah, so this is the design for our absorber and desorber module. Pretty simple from the outside, more complicated than the inside. We have, it's kind of shadowed, so you can't really see it, but these are the supply pipes for the ionic liquid. One is in, one is out. It goes into the center of that location in that channel. It goes through 41 parallel little channels there. And we're currently working on that, but the idea is effectively that the ionic liquid goes through those channels, is vibrated by the ultrasonic transducer, which would be underneath and you can't really see it. And the fins that are separating the channels would vibrate back and forth as well as up and down. And this would try to create the most efficient energy deposition into the ionic liquid to maximize the rate of desorption of carbon dioxide. Then the little red thing on top is just the port for the vacuum pump. And the absorber module, it's a hollow fiber contactor. And the hollow fiber contactor is basically just a long sheet of really, really thin tubes. They're about 240 microns in inner diameter. So really, really thin tubes. And they've been rolled up into a tight little bundle. And then they've been stuck in a tube by our supplier 3M. And effectively now you can shove liquid through these tubes and air on the outside of the tubes, and the air will permeate into these porous tubes, but the ionic liquid can't get out. And so that makes it a really high surface area contactor and really, really efficient for pulling carbon dioxide out of the atmosphere. All right. And then some other areas we've been working in. Garrett's been working a lot of test procedure development over the past month. We have some members working modeling software, so a lot of stuff to do there. That's probably our biggest point of contention on the project so far. And then we're also going to be doing a lot of harnessing and soldering with our ultrasonic assembly and DAC sensors. And then my job as a project manager, a lot of balancing budgets and procurement. Alrighty, so project concerns. These are a lot of our high-level project management concerns. We have a lot more technical specific concerns, but I'll be talking about these because they affect schedule the most. So the ones I circled here are ones that I'm probably most worried about coming this March and April. So I'll talk about the left box first. So the manufacturing component faults and also lead time bottlenecking. We're gonna start ordering all of our pieces and we hope to have them in-house and manufactured by April 8th. So that's a lot of quick turnover there. So we've vetted a lot of short lead time suppliers to try to get our best, our quickest shipping so we can assemble the fastest. But the components that we're manufacturing in-house, especially in the machine shop here, where we have to queue it up with other competition with other projects, basically, we've ordered those materials early and are going to submit them now. So we have that little bit of time buffer. And then also manufacturing failures. We have some hard to manufacture components on the desorber. So we bought spares of that stock just in case the machinists mess up the first time. Also time shortage, phase change, schedule slip. We're shifting from design to manufacturing phase. So there's going to be some ambiguity in like roles and tasks over the next few weeks. I'm trying to mitigate that by just specifically delegating testing and assembly work to each member. Also lack of expertise in training. You know, a lot of our undergraduate members haven't made their full way through their degree progress yet, teaching them a lot of the basic about machining and electrical engineering. So we're reaching out to those shops to get them trained up to try to mitigate that risk. All right, that's all we got for you. Thanks for listening.
Any questions for this team? All right, thank you again. All right, just to wrap up today, for those of you that are not in the class, but considering the class, there are two components to it. There's a lecture component once a week with myself and the whole group like we're doing right now. And that happens usually for 50 minutes once a week. We have guest lectures, we have topics, we have interactions with other teams. We try to make that lecture component something that you get tips and techniques to apply to the projects that you're working on. Plus, we do reviews like we're doing right now. The rest of the time that you spend in graduate projects is with your actual project. So you'll have, I think what works out to be about 4 hours of lab section time per week with your faculty advisor and your team. And then there's other work that happens outside of class, outside of those two types of classes. But on average, the expectation is that you spend about 12 to 15 hours per week working with your team in class, unless you're on Colonel Voss's team. And then you have weeks where they go over 40. Is that true? Like this last week? It's really fun, yeah. Don't let that deter you, though. There are timesheets. There's really no homework. There is a book that you have to read as part of the lecture component, but it's not like a textbook. It's something that hopefully benefits you and your project experience, life experience. I think that's about it for those two different components of the class. And then you get 15% of your grade by the lecture component, which includes attendance. And then the 85% of your grade is assigned by your faculty advisor for the different metrics that they may have on the project, which usually boil down to the things you see there, including peer evaluations and all that. So I'm not going to say it's an easy A class because you do have to work, but it's graduate classes. So as long as you're doing the work and doing what's expected of you, including coming to class, doing what you say you're going to do, you're likely going to do fairly well with the course. I do have a video that's just about a minute. If you'd like to watch this as a former student that took graduate projects, this is my last bit of sales pitch, but if you're interested in graduate projects, you simply send me an email, tell me which project you're interested in. I'll answer any questions. And then once we get through that sort of exchange, I will actually get you directly enrolled in graduate projects. You can enroll yourself. So you just tell me, hey, I really like Astra because I like working every once in a while, 40 hours a week. Then I will work with you to get you enrolled in that class or that section. So I'll stick around and answer any questions, but if you want to watch firsthand, this is a former student, and then we'll be done.
James Mason, and I am a research scientist and engineer at Johns Hopkins Applied Physics that I'm working on and leading NASA missions. I was a student in grad projects in the 2011 to 12 academic year, and then I just stuck with that project, and it became about half of what my PhD thesis was based on. We were working on a CubeSat that ultimately NASA funded. Grad projects is where I discovered the career path I wanted to be on. We launched that CubeSat called Minx from the space station just a week after I defended my PhD. On the actual spacecraft itself, I had laser engraved everyone's names who had worked on it, and that face of the satellite just happened to be pointing at the camera when astronaut Tim Peake took pictures of it being deployed. So I literally got to see my name in space. That was the culmination of years of work I'd done that started in grad projects. I got to be involved in almost every aspect of it: mechanical design, machining and assembly, FEA, thermal modeling and vacuum testing, systems engineering, boatloads of other testing, project management, electrical assembly, ground software development, mission operations, STK orbital simulations. And you know what? I did all those things because they were fun. And objectively, it is so cool to work on a real project. Now I'm the principal investigator for a $9 million NASA CubeSat called Sunset. And I was able to pull off this leadership role so early in my career specifically because of that experience I had that started in grad projects. So I hope that you take advantage of the opportunity that grad projects provides.
Okay, well, with that, I appreciate you coming here. I would really appreciate you taking any leftover pizza and or boxes or this gluten-free stuff. And I appreciate you coming. Thank you all. If you have any questions, please come down and see me. Presenters, you did a great job. Enjoy your rest of your week, and we'll see you next class. Thanks, everyone.